Okay, good afternoon, everyone. Welcome to the second lecture of the second week. Let's get right into it. Not many, I went over a few logistics yesterday, but just to remind you, your labs do start this week. In fact, right after this lecture, there's the first lab. So just make sure you connect to the appropriate meeting, the lab in which you're actually enrolled. And if for any reason you cannot attend the live lab, you can watch the recordings, which should be available perhaps within a few hours after the lab concludes. The spec is already released. It will focus on some of the tools that we discussed in this self-study lab and some of the content we looked at in the first week and even yesterday a little bit. Or maybe, not so much yesterday. It's all based on the content last week. So the experiment, if you look at some of these experiments, they're asking you to compute delays using traceroute and so on and so forth. Right? Okay, so in terms of any other things, please make sure you have joined the ED discussion forums and post any questions you might have here. We are generally pretty quick in replying to your queries, and we would strongly encourage you to use the homework section to talk about the questions that have been posted here, right? In particular, these questions, which we have explicitly asked you to discuss and arrive at a solution. There's a question on tutorials. If you look up the lab schedule, you'll see that it says there are 8 lab sessions, right? And 2 of those lab sessions will run as tutorials. So the tutorials will be in week 5 and week 10. So this is right before your midterm exam and your final exam. So the tutorials are in a sense a way to go through some problem solving exercises that will help you with the exams. Okay, so let's jump right into the content now. We started off looking at the application layer yesterday, and we first spent a bit of time talking about some of the basic principles on networked applications. So 2 sort of things we looked at. One was how do you design the application architecture, essentially whether you go with client server or whether you go with P2P, right? We also briefly talked about sockets and essentially the idea that the socket is an interface that these applications use to send and receive messages from, right? And I'll spend a bit more time on sockets when we get into the transport layer. That should be in week 4. Then we briefly talked about what sort of requirements the applications may have. In particular, we focused on throughput, latency, right? And reliability, whether or not the application requires 100% reliability. And then we looked at, because remember the applications are going to run on top of the transport layer. And as an application designer, you need to pick one of the 2 available transport layers on the internet, which are TCP and UDP. So we then spent a few minutes just talking about what services TCP and UDP provide us, because that is important in order to be able to choose which one you want for your applications, right? Of course, we'll talk a lot more about TCP and UDP in week 4 and 5. Those 2 weeks are entirely dedicated to those 2 concepts. Of course, with UDP, there's not a lot to cover because UDP doesn't give you many services at all. Okay, so now let's start looking at some example applications. And we'll start off with the most widely used internet application, which is essentially the web. And specifically, we'll be looking at the application layer protocol for the web, which is HTTP. So where did the web start? Well, you can trace back the origins of the web right to the late 1960s to this gentleman, Ted Nelson, and the project Xanadu. So he came up with this idea of having a worldwide sort of network where you could have bits and pieces of information stored as separate files, and you could establish links across these files, right? So one file could have a link to another file and so on and so forth. And he actually coined the term hypertext. Okay. Now, for various reasons, which I won't go into, this project never really took off. It failed. And yeah, just let's not bother about the reasons here. However, there was then another gentleman who was working at CERN. So this is the particle accelerator in Geneva. So the people working on that project, they needed to store all sorts of pages, all sorts of documents, and these documents needed to be cross-linked with each other. So essentially various research articles and so on and so forth, right? So in order to provide these, and Tim Berners-Lee was sort of at that time managing the infrastructure for them, the computing infrastructure. So he came up with this idea of being able to have these distributed databases of content, or pages as he called them, which could be then linked to each other using links. And this, he came up, he sort of used that same notion of hypertext essentially. So the first implementation, and of course, he then designed the HTTP protocol, which was essentially responsible for querying this database and obtaining the information, right? So the first implementation was in the 1990s, and he came up with some iterations over the years, as you see here. And pretty much the protocol that we use these days is the HTTP 1.1 protocol. So that's actually been used in use for a lot of years. There is a successor coming through, which is HTTP 2.0, and this has been standardized a few years ago. It's still rolling out. It's not extremely widely deployed yet, but the web is slowly moving towards HTTP 2.0. And we'll talk very briefly about the differences, essentially what new things are added in this protocol, in this version of HTTP later. But most of our discussions will focus on 1.1. Oh, and by the way, you can actually go and look at the first page. Maybe I don't have it open here. So this is the first web page essentially. Now, I mean, most of you on this call or in this course have very likely seen much more creative web pages than this. But growing up, I was frequently used to web pages like this because these were the style of web pages that us oldies used to use at a given point in time. Right? Okay, now if you look at the web, it's actually, or HTTP to be more precise, it's being used for a lot of things than just transferring web pages, right? So this is a nice graphic developed by Laurie Lewis, as it says there, and I think Chad Johnson, I believe. So every year they come up with this nice illustration, which shows you what actually, how much data is being, or what activities are happening on the internet in 1 minute, just 1 minute, right? So you see within 1 minute, there are over 4 million Google search queries happening using HTTP, various app downloads. YouTube also uses HTTP for transferring video and so on and so forth, right? So you clearly see the dominance of the web as or in fact, HTTP as the most dominant application really on the internet, right? So what exactly are we talking of when we refer to the web or HTTP? Well, essentially we are talking of requesting web pages, and web pages, as you all know, consist of objects, right? So the objects can be really multiple things. Typically you would have what's called a base HTML file, and that base HTML file would have multiple embedded objects. So these objects could be images, they could be Java applets, JavaScripts, audio files, really anything that you can think of could be a web object, right? And each object is uniquely addressable by what's referred to as a URL, as you all know, right? This is just showing you a very simple web page. Now, of course, the language to design the web page is, of course, HTML. That's a different language. That's not necessarily part of this protocol. But really, this is the hyperlink as we know it, right? Which is pointing to a particular object, right? And you could have multiple such objects embedded in a page. So the URL is actually more generic and not necessarily just specific to the web or HTTP. The format is as follows. So you can have a particular protocol here, and the protocol could really be multiple things, not just HTTP. You could also have other protocols like FTP, SMTP, and so on and so forth. The host name could either be the name like we use, so www.unsw.edu.au, or you could even type in the IP address of the server that's hosting that web page if you know it. Now, of course, it's not very typical to know IP addresses. For us humans, it's much easier to use the host name, right? Rather than the IP addresses. So almost always we would type in the host name. Yeah. You could also optionally specify the port, but typically it's not again standard to specify the port because web's HTTP servers are always listening on port 80. So that's the default port. And secure HTTP or HTTPS servers are always listening on port 443, sorry. Right? So these are well-defined ports. So you don't really need to specify them. If you are hosting a web server at a different port, then you would need to indicate that port to your users. So again, that's the reason it's not very typical to run servers on a different port, because it makes it less accessible to the wider public. Then beyond that, you of course have the path within directory path. Essentially, this reflects the path within which your resource is hosted on the actual server's operating system, right? So that would depend exactly on where it is stored on that particular server. And then the resource is, of course, the object that's been trying to be fetched. Now, HTTP is the application layer protocol for the web. The web, of course, has many other things beyond just the HTTP protocol. Of course, you have the web pages themselves. You have software for the browsers. You have software for the servers. So there's a lot more involved here. We'll kind of just focus on HTTP, which is the application layer protocol. And HTTP follows the client server model. So we have two separate programs. We have the client program, which is user facing, and based on what the user wants to view on the web, they would type in the appropriate URLs or click the appropriate links. And the browser would then initiate the appropriate request, HTTP request for those web pages, right? Now, of course, the browser, implements the client part of the HTTP protocol, but it also implements many other things like the rendering, because the browser allows you to actually view the pages. It allows you to have plugins for various other applications, like say you're watching a video, then you could initiate a video player within the browser and so on and so forth, right? Then we have the server. The server is again a piece of software program that's running on typically a high performance machine, or perhaps it's even running in servers hosted in data centers. And the role of the server is simply to service the requests. So receive a request, go and fetch the requested object. If required, the server might need to contact another server. If, for example, the request is for something that's not hosted locally on that server, or it needs to query some database and pull out certain requests, if the query is for some dynamic content, and so on and so forth, right? And in the end, the server generates the object and sends it back to the client. So it's a very simple request response message model. It's all that is to HTTP is this. You have requests going through and then responses coming back. Now, the protocol itself is open source, which means, and which is kind of evident here. You can have various different browsers. So there's tens, maybe even hundreds of browsers out there that you could use, right? And similarly, there's tens or hundreds of web server software that you could deploy. I mean, Apache is just one example. There could be others, right? And similarly, you could even have the browsers running on different types of devices, right? So all of this is possible because the protocol itself is open source. So there are specific RFCs that you can look at, which will show you the actual specification for HTTP. And each one of you could actually follow those specs and write your own browser and server programs, which should be able to talk to any other browser and server program out there interchangeably, right? So that's the beauty of having open source protocols. Now, HTTP uses TCP. This is something we discussed yesterday because we want to make sure that whatever objects are being fetched are received reliably. We can't have bits and pieces missing in web pages and so on and so forth. Now, TCP, as we again discussed yesterday, requires a connection setup process. So the client will initiate a connection request and send this connection request to the server's IP address at port 80 or 443, depending on whether it's secure or unsecure. In most of this discussion, we'll just assume plain HTTP. I mean, the concepts still remain the same, be it HTTP or HTTPS. The only difference is before this communication can happen, in secure HTTP, there's a separate TLS protocol exchange that's executed to set up the secure communication channel. Okay, so we'll talk about TLS and HTTPS towards the end of the course when we get into security. So the client initiates the connection, the server accepts the connection. So you can kind of, we'll get into TCP connection setup a little later, but for now, just assume that there's one round trip time delay, essentially, in order required to establish the connection. So connection request goes through, a response comes back, and only at that point is the connection established, and only at that point can the actual HTTP request be sent from the client. So once the connection is set up, then the client can send requests, the server will respond back, and the connection is closed. So one important thing to note here is HTTP by default is a stateless protocol, which means the servers don't actually maintain any information about past clients' request, right? So if your browser keeps asking for the same web page again and again, the server is not going to say, hey, I already sent you that web page, because the server is not keeping track of your past requests at all. Okay. And the reason HTTP was designed to be stateless is simply to keep the server very simple, because remember, the purpose of the server is to service a lot of requests from a lot of users as quickly as it can. So having this simplicity helps the server to speed up that particular process, right? So because maintaining state is very complex, right? Because you're keeping a lot of information, and then if one endpoint crashes amongst the two, then you have these issues of inconsistency in the state, which must be reconciled and so on and so forth. So the designers of HTTP decided, hey, we don't want this. This is not necessary to run the web. So we'll just keep HTTPS stateless. So I know there's going to be a question on cookies, and it just came about. In fact, someone has asked, were cookies specifically deployed to work around HTTP being stateless? The answer is yes. Let's just hold on to cookies for a minute. I'll be talking a little more about cookies in just a few minutes. So let's just defer the discussion of cookies till we get through some of these basics of HTTP. So if you look at the messages, there are really just two types of messages. You have requests and response. And in fact, all HTTP messages are ASCII, which means they are human readable, right? So again, this shows you a bit of the age, because remember, HTTP was originally designed by in the 90s, right? So it's an old protocol, and at that time they somehow thought, okay, having this messages to be ASCII readable is easy because humans can read it, so we can diagnose what may be wrong and so on and so forth, right? So if you look at the request message, it's fairly straightforward. There's a first line which is called the request line. So this is essentially what are referred to as the commands, or what kind of requests you can send. And I'll go over some of the options, but really the main request is the GET request. That's the one that's almost always used, which is to obtain a particular web page. Then you have the actual URL that's been requested. You have the version, and then there's a carriage return line feed. So that's supposed to be the end of that line, right? Below that, you have a bunch of header lines. Now there's no sort of mandatory requirement of which headers to use and so on and so forth. So you might not always see all these headers. Some are commonly used, but it's not as if each and every one of this is necessarily required, right? But these are very typical headers that you'll see in a request. So here you have the host. So this is the host that is being contacted. Let me ask you while I'm going through this, why do you think we need to include the host? Because remember, the TCP connection has already been established, right? As we said here. So let's say I'm going to access this particular web page, net.cs whatever .edu/index.html. So I've already set up a TCP connection with the server that's hosting that particular web page, right? And now I'm sending a GET request for a particular object, right? The web page, sorry, the index.html. So why is it necessary to include this in here? Think about that. Some of the I'll quickly run through the others. So you'll notice some of these are fairly self-explanatory, right? Like language, encoding. This keep alive indicates how long the TCP connection should be kept alive, how many seconds, essentially. And you'll notice for each line, there's a carriage return line feed. And at the end of the headers, there's an extra carriage return and line feed to indicate this is the end of the message in this case, because typically the GET request will have no body. So all of this is just headers. There's no real body within the message. So let's see. Yeah, I think, who's this? Lubo has the correct answer in the feed. So Lubo has said, because a physical server can hold multiple sites. This is the correct answer. Well done. So remember, we talked about web hosting, right? Maybe some of you are hosting your own web pages. It's very likely that you have actually set up your own physical server to host your web page, right? So for example, my personal web page is hosted by DigitalOcean. I'm not hosting it myself, right? Now, of course, DigitalOcean is not just hosting my web page. It's hosting web pages for thousands and millions of users out there, right? So when you're accessing my web page, the index.html web page for www.salilkanere.net, you would have set up a TCP connection with one of the DigitalOcean web servers, and you would have requested for my index page, right? But remember, this web server is hosting the index page for not just me, but for hundreds and millions of other sites, right? So which index.html should it give you? Should it give you mine, or should it give you someone else's? So that's the reason it is necessary to include this, because by looking at this, the server will know, aha, you've asked the index.html for www.salilkanere.net and not for someone else, right? So that's the reason the host header is important, because most websites are hosted by servers which are hosting multiple websites, not just one website, right? The other answers are actually not correct. For the routers, no, the routers don't need to know this. As we said, HTTP is an end-to-end application. The routers don't care whether the messages they are carrying HTTP or not, right? So routers never look at the application layer headers. Authentication, no, not really. There is nothing to do with authentication. That takes place during the HTTP, secure HTTP handshake. It has nothing to do with the headers here. Send the resource back. Well, this is the host name of the server. This is not information about the client, right? Router is in the network layer, yes. So routers do not work on the application layer. So to clarify, does that mean the IPs are exclusive to each server or to each host? Well, what's the difference between a server and a host? It's the same thing, right? Or do you mean by website, by host? I'm not quite sure. Yeah, I think your the terminology host is perhaps not being used correctly here. You probably mean websites, right? Or domains. A host is just a machine. So a server is a host, a client is a host. Could you please turn off your mic? Okay, a server can have multiple NIC holding multiple IPs and multiple websites can run on the same. Yes, that's correct. We'll look at all that a little later. That these discussions are a bit tangential, right? Okay, so that's the request. The response also looks very similar, right? The response will also have a status line. So that's again the protocol. And there'll be something called a status code and status phrase. So this kind of notation indicates the status of the response, right? So normally when you're requesting something and you're getting back the response and everything is okay, you'll see this 200 okay status code and phrase, which is self-explanatory, right? So it means everything is okay. And then you'll again have a bunch of header lines. So the date here indicates the date when this response is being sent. The server indicates the software that's running the web server software. This indicates the last time this particular object was modified, right? So whatever object is being sent here, this is the last time it was modified. This is something which is just a hash of this object, which is called an E tag. So we'll examine these two fields a little later when we talk about caching. Then there's something called content length, keep alive, and so on and so forth. And again, at the end, you'll have an extra carriage return and line field, and then you'll have the actual data, the object that's being requested. Okay. So response, again, very similar, ASCII headers. The only difference would be you would also have some object, because of course it's a response to something, unless of course if it's an error message, in which case you won't have any object necessarily, right? So some of the status codes, again, you might have seen some of these. So this is basically when everything is successful. This is something where the particular object you're fetching has been moved permanently, so it's now being hosted somewhere else. Okay. This can be relevant, particularly when it comes to the discussion on CDNs. So we'll look at that. And then, of course, some of these other ones are self-explanatory, right? So bad request, not found if the object you're requesting isn't hosted by the server. Some of these are, I mean, this one is just a joke. This was put in just as a joke. This really has no real purpose, right? So HTTP is all text, as you very clearly saw. It makes it easy for us humans to read it. There is, I mean, it's very easy to sort of delineate the message /r/n, and there are no issues about encoding or formatting anything. And the object, of course, can be anything. It can be a web page, it can be JSON, it can be video, audio, whatever, right? It doesn't necessarily just have to be text or HTML. However, think about it, having all of these headers as ASCII is not very efficient, right? Because let's say you wanted to send this particular string as ASCII, you would need 8 bytes, right? I mean, this number is essentially as a string, you would need 8 bytes. However, if you stored this as an integer, it would only need 4 bytes, right? So in terms of efficiency of the amount of data, how much information you're conveying purely in terms of number of bits, ASCII is not the way to go, right? And in fact, I believe the next version of HTTP is doing away with ASCII, HTTP 2.0, right? Okay, so there's a few questions. Let me get through them. So there's a question: one host, one server equal to one IP. Well, for now, assume that. In theory, it depends on the number of network interfaces your server has. So technically, you could have servers with multiple interfaces, which would mean multiple IPs. But for most of our discussion, let's just make that simplifying assumption, because that's just easy to go with. The data doesn't have to be HTML. I already answered that. It can be anything really. Headers contain what is determined by programmer, or it has some standard. So yeah, these these are standardized in that all of these have specific meanings, right? So you can't just use random headers, because again, remember, HTTP is an open source protocol. So all these headers are noted in the standard, in the RFC, right? Yeah, and of course, I mean, you can choose which ones to send and receive, but you can't create your own headers, because that would make it incompatible with other instantiations of servers and client program, browsers and client programs, right? Yeah. Okay, so if you look at the request methods, of course, get is the most commonly used one to obtain an object. Post is used when you're uploading a form, right? So sometimes you remember you fill in web forms with all your details. So all that information that you fill gets actually put inside the body. In that case, your body of the request message will have all that information. And the method used will be post. So that tells the server this message is containing certain form fields, which it can then extract and enter into the system, into the database into which it's stored. There's a third method called head. This is mainly used for debugging. So this is when a head request is received for a particular object, the server will only respond with the headers. It will not actually send the object, right? So this is just to test your servers. With 1.1, there's a few additional methods. Some of these are just, again, for debugging, which we won't bother. The two sort of typically used ones are put and delete. So remember, again, sometimes we use your browser to upload files, right? Like you're uploading an image or uploading a video and so on and so forth. So you attach your file and you send it, right? Click send. So that is, in that case, whatever you're uploading gets sent as a put method, right? So in that case, the server which receives this knows that you're uploading some file, okay? And similarly, sometimes you may want to delete certain things. So delete files, like if you're logged on to Flickr and you're deleting certain images. So this is the reverse of that. Essentially, you're telling the server which files you want to delete as you've clicked, essentially. Right. So yeah, uploading forms I already discussed. Typically, this gets done through the post method. It's also possible to upload information using the get method, but typically, when you're doing that, you're only uploading small bits and pieces of information. So sometimes, for example, when you good example would be when you're doing a Google search. If you type in something, you'll notice the URL changes to that. So in this case, you have searched for monkeys and bananas, right? So in that case, whatever you have searched simply gets added to the URL and gets sent using the get method rather than putting this inside a post method. Right? So most web search engines will use this typically. Of course, when you're uploading large forms, it makes sense to use post rather than dumping everything in the URL like this. Is there a difference in speed between get, push, post, put, and delete? Speed? Well, not so much. It's just that these, I mean, they serve different purposes, right? So it's not like, I mean, it's mainly the size of the message, right? So get would be generally a bit faster than post because there's nothing in the body, right? Whereas post would have something in the body. So that requires a bit more time to process. But again, the differences are really minimal, right? Yeah, someone here answered for small requests, get is faster than post, right? So that's the reason these browsers will, these search engines will use this, right? When you're searching for something, because it's just a little bit faster to do that. Okay, cookies. So one of you already mentioned this, and it probably it's kind of apparent to all of you already that, okay, if HTTP is stateless, how does Amazon remember me, right? When you're shopping and so on and so forth or whatever. So of course, early on, as the web started being used very widely for things like shopping and so on and so forth, it became apparent that there was a need to maintain state despite HTTP being stateless by default. And that's where this whole notion of cookies came into play, right? Now, I could do an entire lecture on cookies. I, of course, don't have the luxury to do that. So I'll keep most of these discussions. I'll give you enough and I'll show you some examples to make this point clear, but you could certainly investigate a lot more because there's various different types of cookies out there, and you could spend a lot of time looking at the nuances, right? So I'll kind of stay at the high level a little bit and just give you the generic ideas. So there are 4 components involved when cookies are being used. So there is some extra headers that are included in both the response and request messages for the HTTP request and response messages. There's a cookie file that's maintained on the server. A cookie file maintained in the browser of the user, and also a backend database maintained by the web server that's keeping track of all these cookies. So let me show you a simple example. In fact, there's a picture on the next slide, which makes it more clear. So these are the 4 components, right? So that's the cookie file on the browser of the client. We have the server, we have a backend database, right? And there'll be certain header fields that are sent. So let's say the user, Alice, is visiting Amazon for the first time in her life. So in this case, there's no cookie, or maybe she's deleted the cookie for Amazon, whatever, right? So then since the client, when it's sending the HTTP request to the Amazon server, it does not see a cookie, so it can't include any cookie information because it has none. So it will just send a regular request without any cookie headers. The Amazon server will create a identifier, essentially a cookie ID for this particular user. Let's say that number is whatever, 1678. It adds this entry into the backend database, and it will send this set cookie with that particular ID that it's created to the client in the response. What does the client's browser do? The browser will now add this cookie into its local cookie file. So now here you see there already was a cookie for eBay, but now a new cookie has been added for Amazon, right? Now any subsequent GET requests sent to the Amazon server, right? So imagine this user now starts clicking things on the Amazon website, starts adding things to shopping cart or whatever, right? So each of those actions manifests a GET request. So each of those GET requests would, would include this cookie for Amazon in the guest requests. The server, when they receive this cookie, will be able to match it with their backend. Okay. Now, in their backend, they may not necessarily need to know the true identity as such, but in the case of Amazon, typically they would, because this user would have created an account and so on and so forth. But strictly speaking, it's not necessary to have all that specific information. It's just some identifier of this person, right? Who that person is may or may not be that important for the server. Irrespective, it knows that this person is visiting, is making another request. So it can tailor this response that it's sending based on whatever information it may have about that user, right? So this, for example, allows the server to maintain a shopping cart, right? So as you move through the Amazon website and keep adding stuff, all of that gets associated with this cookie, and it's all sort of kept in that user state, essentially, right? Now, similarly, let's say you finish your transaction with Amazon, you go away. Let's say you visit the Amazon website again, maybe in a week, right? Now, this cookie is still stored in your cookie file. So now that you're visiting Amazon again, that same cookie gets sent to Amazon. Amazon would match this in their database and say, aha, this is the same user. Last week, they went and bought, I don't know, say the computer networks textbook. So maybe when I'm sending them back the Amazon website, I could send, I could include some recommendations, right, based on their past purchases and so on and so forth, right? So you might notice this happening, right? They might, when you log on to Amazon, you might suddenly start getting recommendations based on what you may have bought. So all this is sort of personalization is essentially possible through the cookies that are being maintained. So yeah, let me take some questions. Just confirming, would these eBay, Amazon names be instead the website URLs? I mean, yeah, so do you mean on the client side? Well, yeah, this would obviously, this would normally be the like ebay.com.au, right? Or whatever, amazon.com.au, right? What if we access Amazon as a logged in user? Will it retain the cookie? So in fact, when you log in, so that cookie gets then associated with your user ID, right? So with your Amazon ID. So if my Amazon ID is Salil, this cookie is now associated to Salil, right? So in fact, that gives them a lot more, they can then do a lot more personalization because now they know that this is actually me, right? And in fact, to maintain that logon status, cookies are also used, right? So now they know that, okay, this person has logged in, their cookie is 1678. So for your entire session, they can now track that it's 1678, which is basically Salil, right? Cookies only store header info or it contains client action. Well, what is store? I mean, this is just an identifier, right? So on the client side, it's just storing an identifier. On the server side, well, it really depends what they want to store, right? So they might store specific objects you have clicked on their web page, and so on and so forth. So it's really up to them what they're storing, right? So where it says eBay 8734, would it store ebay.com? Yes, that's how it would be storing. What if we delete cookies? Will data still be stored in the backend database? Yeah, so that if you clear out your cookies, then this information gets lost, right? So now you don't have these cookies at all. So the next time you go back to Amazon, a new cookie would be created. And since you're logging in, typically with these websites, they would associate this new cookie now with your particular login. So yes, some of that past history could be lost, right? Because you have removed the cookies on your end, right? could the cookies even go up to the extent of storing files, images into the backend data server, or only text-based objects? So remember, if you think about it, what is Amazon going to track, right? So Amazon is going to track the things you have purchased, the things you have looked at, and so on and so forth. So, and remember, this is on their system, right? So, I mean, they could really store anything that they wanted to on, and it really depends how they have implemented their website and so on and so forth, right? So they might say, this person went and clicked on these particular objects on my web page. These objects are all, I don't know, CDs for Soundgarden, let's say. So then they can keep all that information, right? Oops. Yeah. Okay. So of course, I mean, this is all good. It's fantastic, right? It allows us to do a lot of interesting things on the web. They're certainly very useful. But there's also a dark side to this. Essentially, cookies will allow individuals, I mean, will allow certain entities to actually track your behavior across the internet, right? And in particular, third-party cookies are notorious for this because they could follow you across multiple websites. And they could, a lot of this is actually used for targeted advertising, right? So these third-party cookies could sort of see that you're browsing ABC. I mean, I don't know. Let me give you some examples. Okay, so you went to the Nike.com, then you went to newbalance.com, then you went to puma.com or whatever. So now they know you're browsing all these sports websites. So the next time you visit another website, you may certainly start getting advertisements from Nike. You may start getting advertisements from Puma and so on and so forth, right? So there's a lot of nefarious things that can happen using cookies. So let me give you a very simple example of this, how they do that, right? How does a third-party server actually track your browsing habits? So look at this very naive example. So I'm seated here. I've visited a website A. Now let's say on this website, there's a particular banner, right? Nowadays, not a lot of websites have banners, but some still do, right? So you'll see on a website, there's a certain advertising banner, right? Now this actual object is not hosted on this particular website. So this object is actually hosted on this third-party website. So DoubleClick is one particular ad tracking network, right? This is actually now owned by Google, but let's just say, okay, DoubleClick, right? So the actual banner is hosted on the DoubleClick server. So when I actually visited this website, my browser tried to, when it saw this particular URL, of course, it's going to send a GET request for this banner to the DoubleClick server, not to this server because it's not hosted here. And what is DoubleClick going to do now? DoubleClick is going to create a cookie for me, okay? And it's going to know that I visited website A because I'm requesting for this specific banner that is hosted on website A, right? So it's now created a cookie. It's got some information about me. It knows I've visited website A. Now, let's say later I go and visit, yeah, so that's what it's saying. It's creating a cookie for DoubleClick, so on and so forth. Now, let's say I visit website B after some time, right? And this website also has a banner. And this banner is again hosted at DoubleClick, right? So on this particular web page, there's a link, essentially an HTTP link that points to the DoubleClick server, right? With the actual image name and the path name and so on and so forth. So when I visit this website, my browser sees this and it then sends a GET request to the DoubleClick server. And since it's sending the GET request to the DoubleClick server, it will include the DoubleClick cookie that's stored on my particular browser. So what does DoubleClick server now know? Well, it knows that this same user, it may not necessarily know it's Salil, but it knows that this user 3445 visited website A and he's now visiting website B, right? And the same thing can keep happening, right? I go to website C again, the same thing happens, right? So now DoubleClick has essentially got a good history of all the websites that I've visited. And based on that information, they could now start feeding me tailored advertisements, right? So rather than have these generic banners, they could say, I've visited Nike, I've visited Puma. So the next time I visit something, they could flash a banner for a Nike ad or something like that. Now you might think ads are harmless, but this is really a problem on the internet these days, right? So in fact, a lot of browsers are now disabling third-party cookies. So which means currently, if you go into your browser, you'll see a setting where you can disable this third-party cookies. So which will ensure that this cookie 3445 never gets actually created on my browser, right? So this sort of tracking will not be permitted by most browsers, right? Of course, as I said, this is only scratching the surface. There's a lot more you can look up about cookies in your spare time. Necessarily, I won't ask you any complex things on the exam beyond what we've discussed here. I will show you some examples though. So let me just quickly go to my Firefox browser, which I've actually set up for you. Okay, so this is in the privacy and security setting here. You'll see there's a standard setting, right, which will, as you see here, it actually disables this cross-site tracking. So it will disable this example that I just showed you. But I just want to illustrate something for you. So I'm going to choose custom, okay? And I'm going to actually just make it completely unsecure. So at this stage, I've cleared out everything, right? So my browser is pretty much now going to store any cookie that it gets, okay? Currently, there are no cookies. I've cleared out all my cookies, okay? Now let's go and visit a website. Let me go to news.com. That is particularly bad and notorious. You'll see it still has those crazy banners and stuff like that. There usually is a banner up here. I don't know what happened. Right, so I've visited news.com. For some reason, this doesn't refresh. Let me try this again. Yeah, there you go. Right, so I just showed you initially my cookies were all empty, right? I visited news.
Okay, Salil, you're muted.
Oh, I'm so sorry. I didn't realize I was muted. Were you able to hear the example I just showed?
Not after you showed us the cookies, like when they've been made.
Thanks. Okay, let me just repeat what I did. Sorry about that. I don't know what happened. Maybe I clicked something while I was moving around all these web pages. Right, so I'm just showing you the Firefox settings here, essentially. Now, normally you should be selecting something like this, the standard setting, which blocks a lot of this third-party cookies and stuff like that. What I'm purposely going to do is select the custom setting, disable all these security features. So at this stage, this browser is completely open to cookies. It's going to accept all sorts of cookies, right? I'm going to clear all the cookies, okay? So I've cleared out all my cookies. You can see for yourself, there's not a single cookie anymore, right? And now let me visit this notorious website, news.com. It's particularly a bad website. I've tested this before because it's got all sorts of banners and hidden cookies, right? You'll always see things like this here, which allows sites like Facebook and so on and so forth to also track you, right? So I've visited this website. Let's now go and see how many cookies are created on in my browser. For some reason, this has to be reloaded, but anyway, okay. There you go. Right. Good point. Thanks. So the previous recording is intact. It's being saved on my computer, so we are all okay. And I've started a new recording here, and I'll splice the two before I upload them. Yeah, interesting things happen in a live lecture. Sorry again. So are there any questions? Well, there's a lot of your comments here. I think some of you have already answered stuff, so I think we are okay. If there are any questions I may have missed, please type them again. What is my background? It's a cover. It's an album cover. There's a Metallica album called Master of Puppets. This is the cover art for that. Okay, so let's talk about performance, right? So of course, as users and even the people who are servicing the web pages, they want to make sure that users can access the web pages as quickly as possible. So page load time is a very critical metric, right? So this measures the time from when you click a particular URL till the actual web page you're requesting is viewed by you, right? And this depends on a number of things. Of course, the content, the structure of the web pages, the protocols involved, and of course the network conditions, right? The bandwidth and round trip time. So the performance goals again depend on the specific entities at play. So from a user perspective, what do we want? We want fast downloads, and we want whatever websites we are accessing to be highly available. From the content provider side, what do they want? Well, they want users to be happy, which essentially is this. They also want to keep their costs down if they can. So they want sort of value for their money, right? They want to be able to distribute their content as effectively as possible while still minimizing costs. Now, the network as such doesn't really come into picture as such, but you could think of it as a secondary factor in this case. And generally, we want to avoid the network to be overloaded, because if the network is overloaded, obviously the users will suffer, and similarly, the content providers will also suffer, right? So let's look at various ways on how we can try to achieve these goals. So how do we get the downloads to be faster? Well, we can improve the HTTP protocol itself to achieve faster downloads. Another thing we could also do is explore the use of caching and replication, which will also help speed up the downloads from a user's perspective. It will also ensure high availability, and it will reduce network overload. And in some sense, it also reduces the costs from the content provider's side. Then finally, we'll also briefly look at CDNs. Basically, how do we exploit the economies of scale to ensure that content can be delivered quickly? So this is more a content provider-centric view, essentially. So how do we improve the page load time? Well, the first thing you could do is reduce the content size, which means you're transferring less things. You use smaller images, you use compression, and so on and so forth. But we won't be talking about that in this course, because that's not really our goal here. What we will certainly focus on is this part. How do you design the HTTP protocol in a way to make better use of the available bandwidth? So we'll talk about things like persistent connections and pipelining. We'll also look at how we can avoid repeated transfers of the same content, right? So content that is being fetched by multiple users, it makes sense to cache that somewhere closer to the user. And so that's where we'll explore this notion of web proxies. And finally, how do we get the content closer to the client themselves? So this is where we'll briefly explore CDNs, right? So almost all web pages do not just contain one file. They will always have the base HTML file, and there'll be a bunch of embedded images or any other objects, right? So how do we retrieve all these objects? So naively, you might say, okay, you retrieve them one at a time. Go and fetch one object, then go and fetch the second object, and keep doing this. Now, of course, if you were to do this whereby you're setting up a new TCP connection each time, then that's obviously not going to be very fast, right? It's going to incur a lot of delays. And the first version of HTTP actually did this. So this is what's referred to as a non-persistent HTTP. So here, each object was fetched over a fresh TCP connection. Then the TCP connection was closed. And if you had to download multiple objects, you would have to set up multiple TCP connections, right? Now, in some of these discussions, we'll use pictures like this. So we'll kind of abstract the rest of the internet. So remember, this internet contains all the routers and so on and so forth that we talked about, but we'll abstract over that, and we'll just consider the end-to-end delay and essentially the round trip time between the client and the server. Okay. And for all these discussions, unless noted, we'll assume the round trip time is fixed. Okay, as noted here. So this is the time for a small packet to travel from the client to the server and back. So by small here, we mean a very small packet. So the time to actually transmit that packet is negligible, right? So a GET request would be a small packet. So the whole process of fetching one object would look something like this. So you first initiate a TCP connection. So remember, that requires a setup message, a confirmation to come back. So this TCP connection itself incurs one round trip time. Next, the file is requested. So the object is requested using a GET request, and then the file is received. So since the file being requested is going to be larger than a GET request, we do need to account for the time to transmit this file. So that's why you'll see there's a bit of thickness here for this line compared to this line. So the total delay to fetch this particular object or this particular file is 2 times the round trip time plus the time to transmit this file. Okay. And remember, this is for one object, right? So in the context of non-persistent HTTP, or the first version of HTTP, HTTP 1.0, you would have to keep repeating this for each and every object, right? So imagine there's a web page with multiple objects. So you would first go and fetch the index file, close the TCP connection. Now the index file will probably contain multiple objects. So for each of those objects now, you would, again, for the first object, you would set up a connection, as you see here, request that object, close the connection. Then again, set up a new connection, request the object, close the connection, right? So you would keep doing this on and on and on for every object. So obviously you kind of hopefully realize that this is extremely wasteful, because what's the point of creating a connection, closing it, setting up a new connection again and again? Why not just keep that connection on all the time and then request all the objects, right? So clearly this non-persistent approach wasn't very helpful. And in fact, as you'll see a little later, you'll see that the way TCP works is it actually goes through a slow start phase where it slowly ramps up the throughput. Okay, so it is actually quite desirable to keep the TCP connection running for a little while so that it can actually start ramping up the throughput. If you keep doing this, where you open a connection, do a small transaction, close it, then you start another new connection, you're starting from scratch, essentially. You're starting with a very low throughput to begin with. So this point will become much more apparent later. So we'll kind of leave it to later for now, right? So obviously this approach of doing things one by one and close is clearly, or doing things sequentially is perhaps not the best thing to do. So you might say, hey, sure, we could still use multiple connections, but you could open them in parallel, right? So rather than doing that sequential one by one request. Once you have fetched the index page, you know how many objects are in the page. So then you could open as many connections as there are objects and send all those requests in parallel across those multiple connections, right? So imagine that index page had 3 objects. So you could set up 3 connections in parallel, and you could send the 3 requests and wait for the objects to come back. Now remember, on the internet, packets can get reordered, right? So as it says here, it does not mean that, okay, if you send, as you see here, right, you're kind of sending these requests almost in parallel, right? So as you see in this picture, perhaps R1 got delayed a little bit, R2 experienced less delay, because these packets could take different paths, right? It's not guaranteed that all of these packets take the same path towards the destination. And in fact, the objects being requested may also have a different, the server might have different delays in fetching those objects, creating the responses and send them. So by doing so, you're certainly, you cannot guarantee the ordering of those objects. And strictly speaking, the ordering may not even be important on a web page. Sometimes it is, sometimes it's not, right? So this is not really a big issue. There is another problem, however, with parallel HTTP connection. So what do you think could be the potential drawbacks of opening too many parallel HTTP connections with a web server? So could you please open Zeetings and answer this question? So if you could go to zeetings.com/Salil and kindly answer this question. I think you'll have to type in something, because this is not a, just type in a very short sentence if you can. Yeah, I think some of you are answering. You're kind of highlighting the key point. This is basically the answer, right? Because what you're doing, remember the TCP, right? TCP, as we discussed, requires the endpoints to maintain state. So if a single browser is sending multiple parallel connection requests to the server, that particular server now has to keep track of these multiple connections for each individual browser, right? So if each browser is opening 10 connections, then the server has to keep track of these 10 connections for each client, right? So that's certainly a lot of work that the server has to do, because it has to keep that state and manage that state, right? So it incurs essentially a lot of work on the server. It overloads the server. So that's the reason you typically want to limit this. Okay, so certainly there are benefits, but we do need to be aware that there are some potential problems with this as well, right? Okay, so let's move on now. So given that we don't want to keep closing connections and opening new connections, right? So the next logical step in the evolution of HTTP, which is the current version of HTTP that's used, is this notion of keeping the TCP connection active, right? And requesting all objects that are required on that same connection. So since we are keeping the TCP connection persistent, this is called persistent HTTP, right? Very simple. And there are various benefits to this beyond just reducing delay. So as you'll see later in this course, TCP does a lot of things which require it to be running for a considerable amount of time. Like TCP has an algorithm which tries to learn the round trip time, which can be very useful to how it functions. I talked about how TCP starts off with a low throughput and slowly starts to ramp up, right? Which is basically called discovering bandwidth and so on and so forth. So all of these mechanisms of TCP actually benefit from that connection being active for a little longer than just sort of simple request response interactions. So with persistent HTTP, again, you have two options, right? So certainly you can keep the connection open and then send all the requests. Now the question is, how do you manage those requests, right? So you first go and fetch the index page. Now you know that this index page has X number of objects embedded. So now do you request each of those objects serially, or do you send all the requests back to back, hoping that the responses will also come back to back, right? So those two options are indicated here. So the first one shown here is without pipelining. So in this instance, you are still making serial requests over that same TCP connection. So you request one object, you wait for it to come back, then you request the second object, and so on and so forth, right? So in this case, it takes about 1 round trip time for each object, plus whatever time is required to transmit the object, right? In contrast, if pipelining is used, you can certainly save time, because what you're doing now is sending all these requests back to back, and then the response side should hopefully arrive also back to back, right? So if you compare this with this, if you look at the delay, it's about 1 round trip time plus whatever time is needed to transmit the objects, right? So this is much faster than doing serial fetching of objects. And that's precisely why the default option in HTTP 1.1 is to keep the TCP connection open and to use persistence, which means as soon as the browser knows how many objects are embedded in a particular page, it will send out all those requests back to back and hope that the responses will also arrive very nicely back to back, right? So if you were to again draw this using that timing diagram, if you had a web page with 1 index page and 3 embedded objects, this is how the timing would look like, right? So you first initiate a TCP connection that incurs 1 round trip time. Then you fetch the index page. Remember, first you always need to fetch the index page, because without fetching the index page, you would not know how many embedded objects are on that page, right? So there's 1 round trip time plus whatever time is needed to transmit the index page to get that. At this point, the browser knows there are 3 embedded objects, so it can request them back to back, and then these objects arrive, right? So the total delay would be 3 round trip times plus whatever is the time needed to transmit these 4 files, essentially, right? So there's some quiz questions later, which I'll get to, which examine you on this. So these are kind of good questions I could ask you on an exam. Okay, so that's one thing, right? We could change how HTTP actually operates by using persistent and pipelining to speed up the process. Another thing we could also explore is to make use of caching. So by caching here, we mean rather than fetching the same object again and again from these origin servers, we try to cache this object locally, essentially somewhere close to the clients, so that if the same request is made again, you can service it from that local cache rather than from the actual web server. Now, of course, your browser also implements this, but this discussion is not focused on the browser, but rather a separate web cache, essentially, right? Now, of course, caching only works if there's what's referred to as locality of reference, in that multiple people are requesting for that same object. Multiple people on the same network are requesting for that same object. If not, it doesn't work, right? Because if there's only one person requesting for an object, there's no point caching it. So it works in some instances, not always. It doesn't work if the objects being requested are dynamic, right? So if the request you're getting is based on certain specific information, if it's something personalized to you, for example, right? Like when you visit Amazon, whatever you receive is personalized to you. So now there's no point caching that, because that is personally tailored to you, right? Some other user is not necessarily going to benefit from all of that information. So when there are dynamic things involved, caching doesn't help. If it's the same thing being serviced to multiple individuals, then it certainly helps. One good example where caching helps is video content, right? Because videos are typically not tailored. They're the same videos that we all watch. So if multiple people are viewing the same sort of content, then it's certainly helpful. So there's a question, is this local storage in React? Not, as I said, here we are more talking of networking entities that we introduce, not so much caching that's done on the end systems. I mean, that is still valid. It's still a cache, and the same ideas kind of are relevant, but here we are really talking of caches that sit like this in the middle between the end, the clients and the origin servers, right? Yeah, and as someone said, this is something that's manually managed. So here we are really talking of an external entity. Of course, as I noted, your browser also does some caching. And again, the same principle applies generally, but our discussion will focus on a separate entity like this, which is, it's often referred to both as a web cache or a proxy server. They kind of mean the same thing, right? So now the way this works is your ISP would install this proxy server in your network, which also means all web requests essentially should be first sent to the proxy server. So anytime someone requests a particular web object, that request first gets sent to the proxy server, right? So as soon as the proxy server receives this, it will first check if it has that object cached locally. If not, it will then request the object from the origin server, which will then service the object. At this point, the proxy server can cache it and also send it back to the client that requested it. Now, if at a future point in time, another user on the ISP requests for that same object, it can be serviced locally. So in this case, there's no need to fetch it from the origin server. So this has done two things. It has saved the delay, right? Because now to service this client, we don't need to go and fetch that same object from the origin server. So that's one benefit. The second benefit is it has saved the bandwidth, right? Because remember, your ISP is also paying the higher tier ISP for its network connection. So all the traffic that's being generated is being measured, it's being counted, and it's been accounted for, right? So since the request has been sourced locally, there's no need to send this request out. So there was no traffic generated on the outgoing link for your ISP, right? So it's kind of, the benefits are dual in this case. There's a question, cache works if it's still HTTPS. So that depends on the objects being fetched, right? If things are being encrypted end to end, then obviously no, it wouldn't work, definitely, because you cannot cache encrypted things, right? So yeah, you're right in that if the objects are encrypted, then caching doesn't help, right? So remember, the real benefit of caching is only for content like videos, I mean, things which everyone is accessing, right? Anything that's personalized to you, there's no real benefit of caching that. So if you saw in that interaction, the cache is acting both as a client and a server, right? So from the perspective of the end users, when a request comes in and the cache services the request, it's acting as a server. But when the cache is requesting for something from the origin server, it's acting as a client, right? So if you were to design a program to run this cache, you would be implementing both a server part and a client part, because it's doing both these things, right? And caches are often installed by ISPs because simply they're cheap, right? I mean, it doesn't take a lot of money to buy a simple server and add some storage to it and make it run as a cache, right? So it's a small investment, relatively small investment for most ISPs. So it's not too much overhead to install this because it can certainly reduce the response time. And as I said, it reduces the traffic on the institution's access link. Now, do remember that caches are deployed by ISPs. So they are not actually deployed by the content providers. So content providers don't have a lot of control over how caching works. There are certain header fields that are used by caches when they send out requests and get responses. So there can be some control, like the content provider in the HTTP response, it can indicate whether proxies should be caching certain objects, how long they should be caching the object, and so on and so forth. So certainly there are some additional header fields that can help with caching decisions, but that's the only control content providers can actually have. So now let's look at a concrete example to see how caching can actually help, right? So there's a bit of very simple math here. It's nothing complex, right? So let's make some assumptions here. Let's assume there's an institutional network. Let's assume the local area network here is very fast, 1 gigabit LAN. Let's assume this institution is connected to an access router using a 1.54 megabit link. And then here we have the rest of the public internet, including the origin servers, right? So we'll assume all objects are of 100 kilobits that are being requested. We'll assume this network generates 15 requests per second, okay? And we assume this will result in 15 responses coming back per second, okay? That's just a very simple assumption we're making. 15 requests go out per second, 15 responses come back every second, right? And remember, these 15 responses will each contain objects of those size. So the total incoming traffic essentially here will be 1.5 megabits per second, right? 15 times 100 gives you 1.5 megabits. So the total incoming traffic on this network and even on this network essentially is 1.5 megabits. We assume that the round trip time from this access router to the origin server that's hosting these objects and back, the total round trip time is 2 seconds. So the time on the latency on the public internet is 2 seconds essentially. Okay. So what's happening here? If you look at the total traffic being generated, right, it's 1.5 megabits. So if you look at the utilization of the local area network, 1.5 megabits divided by 1 gigabits is fairly low. So the utilization of this local area network is very low, only 15%. So that's fine. However, if you look at this access link, right, we said there's a total of 1.5 megabits coming in every second. And if you look at the capacity of this link, it's almost the same, 1.54. So the utilization of this access link is almost 100%, right? And if you recall earlier, we had seen that figure, right? When the network utilization is at 100%, the queuing delays can increase exponentially. Last week we saw that particular picture. So this is actually very bad. If you have an access network like this, which is always operating at 99% utilization, it means the delay on this link is going to be extremely large because there's a lot of queuing happening. Okay. So if you look at the total delay to fetch these objects, there are 3 components to the delay. There's a delay incurred on the institution network, there's a delay incurred on the access link, and there's a delay incurred on the public internet. Now we've been told the delay on the public internet is 2 seconds, and we need to figure out the other 2 delays, right? Now we are not really looking for exact numbers here. We are just looking for some sort of ballpark estimate of what would those delays could be. So given that the institutional network has a 15% utilization, you can sort of go back to that picture and see that the queuing delay in that sense is going to be extremely low because 15% is hardly any traffic, right? So you can estimate that the delay on the local area network is going to be a few microseconds, very low. However, the delay on this link can be as high as several minutes. Why? Because the utilization of that link is 99%. And as we saw, the queuing delay shoots up a lot, right? So which means this is quite bad. This sort of network setup is actually very bad because you're going to get delays of several minutes to fetch objects. And obviously users are going to be very unhappy due to all of this, right? So the access network is essentially a problem here. This has become a bottleneck in this case, and a severe bottleneck. So how could we address this problem, right? So one thing we could do is we could increase the capacity of this link because we know that is a problem, that is a bottleneck. So let's increase the capacity 100 times, right? So the access link rate is now 154 megabits, right? Everything else still remains the same. So what happens now? The LAN utilization, of course, stays the same, but the access link utilization has now gone down from 99% to 1%, right? Which means this access delay has gone down from minutes to milliseconds or perhaps even microseconds, right? So we have kind of increased the capacity 100 times, and we have brought down the queuing delays to extremely low or practically no queuing at all. And that means the total delay is now really just the delay incurred on the public internet and some minor delay here and some very minor delay here, right? So yeah, we have solved the problem. But what has the cost incurred? Well, the cost incurred is that this institution now has to pay a lot more money because they have now subscribed to a link which has 100 times the data rate that it was previously subscribed to, right? So sure, we have fixed the problem, but we have increased our costs, right? And this is a recurring cost. You're paying this on a monthly basis, right? So can we avoid this cost and still be able to solve the problem, right? So that's where caches come into picture. So now imagine the same setting as earlier. So the same slow connection as we had before. But what we have now done is we have put a local cache here on the local network, right? So now how does this solve the problem, right? So in order to solve this problem, in order to come up with some estimates, we need to figure out how many of those objects being fetched are being cached, because without that, we would not be able to come up with an actual number, right? So we need to know what's called the hit rate, right? So how many requests are being serviced locally in the cache, which is referred to as the cache hit rate, which means you have found the object that's being requested. So let's say, just for the sake of argument, the cache hit rate is 0.4, right? So which means 40% of the requests are satisfied at the cache and 60% are satisfied at the origin servers, right? So how does this change things? Well, this means that only 60% of the requests need to go out. And obviously then only 60% of the objects are being fetched from the origin servers, which means the capacity, the load on this link is now 60% of the original load, which now brings it down to 0.9, right? So if you do the math here, you'll see this utilization of this link now comes down to 60%, right? Which is considerably lower. And again, if you go back to that graph of the queuing delay, you'll see this brings down the queuing to something that's much more manageable. It's a fairly low number. There's still some queuing, but it's not a lot, right? So now what's the total delay to fetch these objects, right? So remember, 60% of the objects still need to be fetched from the internet, right? So you need to factor both the objects that are fetched from the internet and the objects that are fetched locally, right? So 0.6 times the delay from the origin servers plus 0.4 times the delay when satisfied locally. So what is the delay when we are fetching objects from the origin servers? Well, it's going to be something slightly greater than 2 seconds, because 2 seconds is the delay here, plus some small delay here and some small delay here. So let me just approximate that as 2.01. Okay. Don't worry too much about the precise number here, just something greater than 2. And then for the other 40%, since they are serviced locally from this local area network, that delay is going to be only a few milliseconds at most, right? So if you do this math, you'll see this delay is only about 1.2 seconds, right? The total delay for fetching these objects. And in fact, this delay is now shorter than this delay, sorry, when we installed this fat link, because here all objects still need to be fetched from the public internet. So the delay for everyone is going to be 2 seconds. Whereas here, by having this local cache, whereby 40% of the time we are servicing objects locally, we have now brought down the delay to a very small number, right? And all we did to do this was install a cache, which is a one-time cost. So you buy this hardware, you put it in your network, and that's it, right? So it's a much cheaper solution to that problem. Of course, the assumption being here, you're being able to get a cache hit rate of 40%, right? Now, whether or not that is realistic is something to debate. It really depends on what content is being accessed in a network, right? If people are watching a lot of videos, then sure, having a cache helps, right? And if because typically people tend to watch what are referred to as popular videos, right? So caching those popular videos is certainly helpful, right? Let me look at some of your questions. There's a question about it being 97%, 99. Yeah, I mean, again, don't fixate on the precise numbers, right? Here, the point being made is not so much the precise numbers, but the concept. The improvement in bandwidth of the access link, is that a physical improvement? Well, it's like you're subscribing to a faster connection, right? That's what I mean there. So it could very well be you're changing from ADSL to fiber or whatever, right? Yeah, what if the content is out of date? Yes, I'll talk a bit about that in the next slide. So please hold on. What sort of content can be cached? So as I said, it only makes sense to cache things that are not dynamic or something that is not encrypted. So videos are always good examples of things you might want to cache. What is the delay of the LAN? Well, there will be some delay to transmit things on a local area network, right? Even if it's being fetched locally, it can't be transmitted instantaneously. You're still going to have to send a request to this cache and get back the response. It's just that this network is very fast, so that delay will be very slow, right? And yes, cache is not suitable for things that keep changing. As I said, dynamic content cannot be cached, right? Why would the utilization rate affect the delay from the origin server? Because you're only servicing 60% of the requests from the origin server, right? As shown here. So since you're only servicing 60% of the request, only 60% of the objects are coming back, right? So the total incoming load now reduces to 0.9 because the other 40% are being sourced locally, right? So the total delay is an expected value. I don't quite get that question. If you mean an approximate value, yes, these are approximations, right? The actual numbers are just approximations. Because I haven't given you precise information to be able to compute some of these minor numbers, right? That's all. Okay, so let's go to the question of cache consistency, right? Or the question that was raised here, how do you know the object that is being cached is still fresh, right? What if the origin server has changed the object at a later time, right? So there's a way to kind of do a quick check on that. So this is called a conditional get. And as I said, there are certain headers which I won't be talking about. There's something called cache control headers. So whenever the server sends an object, the origin server sends an object, it can include some of those cache control headers to give some hints to the caches as to how long they should cache objects, whether they should cache objects at all. For example, if it's dynamic content, you could say, don't cache this, right? Or they could say you could cache it, but each time someone requests it, please check back with me. So that's essentially this conditional get, right? So the goal here is to do a quick check with the origin server to see if the content has been changed, right? The way to check that is if you go back to one of the earlier slides where I showed you the HTTP response message, there's a field called if modified since, right? So that value essentially is the last time that particular object was modified. So imagine that this client here is essentially a cache, right? So let's say some client on the local network has requested for an object to the cache. So the cache can now do a quick check with the server, with the origin server, and say, hey, essentially what it's saying is, hey, I've been asked for a particular object. This is the last time that object was modified. Do you have a fresher copy? So that's essentially what's happening here. The client still send the cache still sends a HTTP request to the server, but it includes the previous if modified since time. If the server hasn't modified that object since that time, it will send a response saying not modified, right? Now, of course, this still incurs a whole round trip time delay to contact the server, but at least what we have done by doing this is we have saved on the time to actually transmit that object itself, right? Particularly for large objects, this makes sense, like objects like videos, for example, right? So even though you're still incurring that round trip time, you have at least checked that the object is fresh and you don't have to necessarily fetch the object back, right? If the object was modified, then the server would have actually sent back the modified object in this case, right? So this is what's referred to as a conditional get. Now there are two ways to check this. One is through the use of this if modified since field. There's another field called an e tag. So e tag is actually useful for checking things that might be dynamic. So it's still a way where you could say, hey, I've cached this dynamic content, but I still want to check. I don't want to serve this content directly because it's dynamic. I should be able to check with the origin server whether this content has been changed, right? So the way to do that is then not rely on these dates, but rather take a hash of the original content and store that as this e tag, right? So later in time, if someone requests for that same content, the cache could send this conditional get request, and it could include this e tag with it. So the origin server can then quickly generate that dynamic content again, compute the hash, and check it against this e tag. If they match, it knows it's the same content, that dynamic content hasn't changed. And in that case, it would send back this same 304 request saying it's not been modified, right? So the e tag is generally preferable when you have dynamic content, because you're just taking a hash of that content, and then that hash can be essentially used to do the check, rather than, because with dynamic content, you probably don't want to use dates like that. Okay. Yeah. What else? So another way so we've looked at two things here, right? We've looked at how to improve HTTP itself. We've looked at caching. Another strategy is replication, right? So this is something that content providers actually do. So rather than hosting things on single machines, they would want to spread they would want to host their websites on multiple machines, right? Try to get the content as closer to the clients as possible. Now, the problem with that is for individual web content providers to do this is very costly, because they would have to go and deploy physical servers all across the internet. Now, companies like Netflix can do that because they can afford it. Google can do that. But if you were to set up a company, it's a small company, you couldn't do that, right? You couldn't simply afford that. So in those instances, there are other companies who provide all of this as a service. So those companies are called content distribution networks, or CDNs. And their sole purpose is to provide other sort of content providers a way to get their content as close to the end users as possible, right? So these content distribution providers, they host a lot of servers all across the web, right? So companies like Akamai, in fact, Google itself provides this service as well. LimeWire, Cashfly. There's a host of these content providers out there, right? So what they do is they deploy all their infrastructure all across the internet, and whenever someone queries for a particular object, they try to direct your query to what are called replicas, essentially replicated servers that are hosting these contents, that is as close to you as possible. By as close here, we mean close in terms of network distance, right? Which kind of also means geographical distance, right? So if your requests are if you're requesting objects from your home in Sydney, you would be redirected to content servers that are somewhere in Sydney in the vicinity, right? So you can essentially have a reduced latency to fetch those objects. If you are making those same requests from China, you would be redirected to servers that are hosted in China, and so on and so forth. So yeah, these companies, they use a lot of intelligent algorithms. So it's a combination of what's called pull and push. So pull is when objects are serviced in response to clients' requests. So as we saw with caching, right? Whenever you get a request, you fetch the object from the actual origin server, and then you cache it everywhere else, everywhere in the network, right? Sometimes these networks will also try to push content explicitly to their replicas, knowing how certain content starts becoming popular. So if they see certain videos are becoming more popular, they'll start putting those videos everywhere on their servers because they expect a lot more users to access those videos, right? So there's a lot going on in this CDN context. I'll talk a little bit more about CDNs when we get into DNS, but for now I'll defer that discussion. Okay? We'll come back to that in the context of DNS. Now you might ask, what about security, right? So HTTP itself is completely insecure. There is a basic authentication, but that's really very naive. So no one uses that. There is a way to do secure HTTP by essentially what you're doing is you're first setting up a TLS connection, a transport layer security connection between the two endpoints, and then running HTTP on top of that. So this provides you authentication. You can also do end-to-end bidirectional encryption. And almost all websites these days have migrated to HTTPS simply because it makes sense. It's easy to do. There is infrastructure out there. All browsers support it, and so on and so forth. Right? Now, there's still an issue with HTTP, which is referred to as HTTP head of line blocking. Right? So despite using persistence and despite using pipelining, there are still a number of problems. So I'll talk about head of line blocking in the next slide. But there are also some other issues, right? So browsers still, despite using persistence and pipelining, they're still opening multiple TCP connections. Almost all browsers do that, right? And as we already noted, that creates a lot of load on the servers, so it's not really desirable. HTTP headers are already very big, as you've seen. There's a lot of header information. It's especially if you're requesting small objects, there's a kind of it's quite wasteful. And some of the delays could actually be improved. So for example, these days there are a lot of dependencies across objects. So it might actually make sense to first fetch certain types of objects, for example, scripts, and then fetch the other objects on the web page, and so on and so forth. So essentially you might want to give certain priorities to the various objects that are being hosted on the web page. And you might also want to allow the servers to proactively send objects, which they know the clients would be requesting. So all those mechanisms are not in place in the correct version of HTTP. And that's where HTTP version 2 is coming up, it has sort of addressed those problems. They've come up with methods to address all of those problems. So what is head of line blocking, right? So despite being able to send multiple requests on the same connection, as you saw here, and despite being able to send them back to back, if you look at the basic version of HTTP 1.1, the request are still serviced sequentially by the server, right? So here, for example, these, you see two requests being sent, one for the base HTML and one for a CSS file, right? Now, normally the server could obtain the CSS file much quickly and send it back. But since the CSS file was requested after the base HTML page, the server will first go and fetch the HTML page and send it, and only then will it service the CSS response, right? So essentially, this second object is blocked by the first object because they are being processed sequentially by the server, right? So this is something that HTTP 2 actually avoids. So HTTP version 2, the original concept actually came from Google. They developed a protocol called Speedy, which has now since been adopted in HTTP version 2 essentially. So it incorporates a lot more improvements. So things like it makes use of binary headers instead of text. It does multiplexing, which avoids this head of line blocking. So fast objects can actually bypass slow objects. It will also prioritize certain objects over others. It does header compression. It allows servers to push objects and so on and so forth, right? So it saves a lot of delays. So you can have a look at this demo. It kind of gives you a bit of feel for that. Now, mind you, I'm not going to ask you questions in the exam on HTTP 2. This was just to give you a quick peek into HTTP 2, right? So what we'll do now, I know we are getting close to time. So if you might just quickly run through these quizzes and then we'll end the lecture, right? So let's just quickly run through these 3 quizzes. So please bear with me. Just because of that disruption, I'm running a bit longer. It shouldn't take more than 5 minutes. So what do you think is the answer for this? So it's saying, okay, consider an HTML page with a base file of size S0 bits and n inline objects, each of size S. Assume a client fetches this page across a link of capacity C and a round trip time of D. How long do you think it would take, assuming we are using non-persistent HTTP without any parallelism? So the first version of HTTP, where you keep opening a new TCP connection for each object. So the really slow one, essentially. Okay, let's have a look. Okay, that's fantastic. Actually, the majority have got it right. So now the way to address, solve these kind of questions is always to use a timing diagram, right? So something like this will be very helpful for you. Now, in this example, I'm assuming because I have to draw something that is tangible. I'm assuming n is equal to 2, right? So since this is non-persistence, we first set up the TCP connection, right? Then we request the base HTML, which we obtain here. At this point, we close the connection. Then we set up a new connection, request the first object, get the object, request the second object. Close the connection. Then we set up another TCP connection, request the second object, get it. Then close the connection, request a third, set up a third connection, request the third object, right? So you notice for getting the base index page, there's a delay of 2D plus S0 by C. And then for each object, the delay is 2D plus S by C, right? So that's where you get this particular answer, D, 2D plus S0 by C to fetch the index, and then 2D plus S by C for each object times N. Okay, so that's the reason the answer is D. I will include this picture in the slides. I will upload a fresh version of the slides with this picture. Right? Let's look at the second one. So it's the same setting. The only thing that has changed now is we are using persistent HTTP, but we are not using pipelining. So here by persistence, we mean we are maintaining the TCP connection, but we are still fetching objects serially. Okay, that's interesting. My answer would have been E, and I'll show you why on the next slide actually. Right, so as before here, I'm using n equals 2 as an example. So we first set up the TCP connection, then we request the base HTML, we get the base HTML. At this point, we know there are n objects. So then we start requesting them serially over the same connection, right? So we don't close the connection now. We request the first object, we get it. So that's D plus SC. Then we request the second object, D plus SC, and this would happen n times, right? So the total delay would be 2D plus S0 by C plus n times D plus S by C. So that would be E. So that's the reason my answer is E. Right? And now let's do one last one and then we'll call it a day. So the same setting. Except now we use persistence with pipelining. So the only difference between this and the previous question was this is now using pipelining. That's interesting. My answer would be D. And let me show you why. Okay, so if you look at this, again, we open the connection, request for the base HTML. So that's 2D plus S0 by C. Now, once we have the base HTML, we know how many objects are there. So we can send all n requests back to back. And then we get all the n objects back to back, right? So the total delay is D plus D plus D. So that's 3D plus S0 by C plus N times S by C, right? So that's the time to transmit each of those objects. So that's the reason my answer would be D in this case, right? So yeah, hope, sorry for keeping you a little longer. I hope that made sense. I'll hang around for a minute or two if there's any questions. If not, have a wonderful week. And I'll see you all next week. Bye-bye. And while you're going out, I'll show you a joke. I couldn't show you this joke earlier. I could have done that in the break. I'll have few more jokes next time for sure. Have a good evening. Bye.